All right. Okay, so this is the homework for electromagnetic wave and polarization. Yeah.
Mm-hmm.
Right. So the first question, which statement correctly describe Maxwell's contribution to electromagnetism? So the correct answer will be C. Right. So he predicted that an oscillating charge produces electromagnetic wave. The other answers, for example, A says he performed experiments to produce electromagnetic wave. That was not his contribution. This was from Hertz. Yeah. B
Mm.
was to say he performed experiments to verify that light is an electromagnetic wave. Uh, no, he didn't perform any experiments, so A and B are just wrong. D says he predicted that the electromagnetic wave did not require a medium to propagate. That was not proven by Maxwell, and he didn't predict anything as well. Okay,
Okay.
so the right answer will be C. Question 2 says the unpolarized light is incident onto two consecutive polarizers as shown. The transmission axis P1 is vertical to the transmission axis P2. Is vertical, and the transmission axis P2 is to the angle 60 degrees from vertical. Okay, so we've
Mm-hmm.
got unpolarized light passing through the first filter. Remember the intensity reduced by half, and then Malus's law apply, cosine square of 60. Okay, so this will just be, so I2 here would just be I0 over 2 times cosine square 60. Cosine 60 is a half, cosine square of 60 is a quarter, multiplies by another factor of half. That gives me 1 over 8, which is
Mm.
0.125.
Yeah. Okay.
Question 3. We have this is the interferometer from Michelson-Morley experiment. Right, have we
Mm-hmm.
talked about Michelson-Morley experiment? Yeah, so this experiment was to try to prove that ether does not exist. That was one of the experiment that shows it. What behavior of light were used by this contemporary method? So we can see these mirrors to reflect, and then we can see when the lights are split using this mirror to two directions, and then coming back on a line together. We also have interference, right? We're supposed to have interference pattern shown on the screen. So it's reflection
Oh.
and
Okay.
interference. Okay. Right. Yeah, and question 4 says which behavior of light cannot be explained by the model proposed by Huygens? Will be polarization. Okay, so Huygens did say light is his principle was used to show light is a wave. He could not show that light is electromagnetic, and hence polarization was not a thing.
Okay.
The other wave properties such as diffraction, refraction, and dispersion, these are can all be classified and justified using Huygens principle.
Okay.
Question 5, this shows you the Foucault experiment. We've got a rotating mirror, okay, and light is going in and then reflected, and then during the time where light sort of go this round trip, right? The mirror has rotated some angle, and then it's being reflected at some angle, okay? And we could measure the magnitude of this angle, using this angle to figure out how much is the speed of light. Okay, so Foucault repeated the experiment by passing the same beam of light through a tube of water. So a tube of water is placed here, right? Water would causes refraction to the light, and which increases the speed of light. Decreases the speed of light. Okay, that
Yeah. Okay.
means light takes a longer time to proceed through the water medium. Therefore, the angle gets to be larger because it can travel a longer time. Okay,
Okay.
it becomes larger. Question 6, which statement correctly describes the relationship between light speed and the measurement of distance and time? Yeah, so this was our definition of 1 meter. Because light was such a constant, and we have to sort of modify our definition for 1 meter to make sense of light. So now we say 1 meter is equivalent to speed of light travels in duration of 1 over c seconds. So that times by speed of light is equals to 1 meter. Okay, so 1 second is the time taken for light to travel c meters. It's just the reverse way to say that. Okay. Does that make sense?
Yeah.
All right, so question 7, we've got a beam of light passes through two polarizers, and the second polarizer has a transmission axis that's 45 degrees to the first one. The intensity of the light beam before and after the second polarizer is I1 and I2 respectively, which row of the table correctly identifies the value of I2 over I1 and the model of light demonstrated by this investigation. So, um, yeah, so it's like 45 degrees, right? So you just
Yeah.
cosine square 45. That's your original intensity computes to the second intensity. So I2 is equals to I1 times this. But cosine 45 is square root of 2 on 2, and square it will be a half. Okay, so it'll be 0.5 of initial, and it shows you the wave model of light. Okay?
Okay.
Yeah, don't forget about the square. If you didn't do the square, you will end up with 0.707, and that's wrong. Question 8, we've got another polarization question, in which case we rotated the second polarizer to sort of create a sort of variable where this angle sort of changes continuously. And we know that the intensity coming out of it is proportional to some sort of cosine square function. And this function would look like something of the shape of D. Okay, you start at maximum when you are parallel, and then you sort of reduce when you are perpendicular. This would be 90 degrees, by the way. And then you would jump back up, okay?
Okay.
It's not going to be C, all right? Because a cosine square function is still like a sinusoidal wave. So, all right. So, question 9 is this is the Romer's experiment where he observed the duration of Io's eclipse at different locations of the Earth and using the difference in the measured time to calculate for the speed of light. Okay. So the question says to which point A, B, C, or D that Earth would observe the time to be like different, right? So if we so he repeated the measurements by recording the time for Io to complete the same number of revolutions around when Earth was at point B, C, and D. But the observation of time would be longer if it measured at D. So yeah, so at D, this is when the Earth is sort of moving away from Jupiter. So like the light that has to travel a longer distance to reach, and then has to like sort of chase the motion of Earth, right? That
Yep.
creates an extra distance and will be longer to measure at D compared to when it's at A. Okay. So yeah, and then question selection A says will be identical in all points. That's wrong. Okay, it won't be identical because the relative motion of Earth and Jupiter would be identical to be measured at B and C. So at B and C are actually not identical because at B, Earth is sort of moving towards Jupiter and at C is moving away. So at B, the time will be smaller, C will be like larger. And C is direct opposite to selection D, so the right answer is D.
Okay.
The last one, so yeah, so currently this intensity will be 0 if, like, I mean, they are perpendicular, so nothing comes out, yeah? How do I reorientate this experimental setup so I make the smallest change to the value of IF? Okay, so A says to rotate the transmission axis of the first by 45 degrees. So that would end up with like a 45 degrees angle afterwards. So yeah, this would be that. So if you look at selection C, which says to reorientate the beam of light such that the polarizing axis is rotated by 45 degrees. So that's just not rotating any of the axes itself, right? It was just rotating the laser beam. Okay. But that doesn't change the fact that they are sort of still perpendicular when it starts to come out, right? So
Yeah.
you're
Okay.
still
Okay.
gonna get 0 no matter how you rotate
I
the beam
see.
of light. So it's C. C is the right answer.
Okay.
Okay, so continue with question 11. Since the outline contribution made by Maxwell, and then we did like this 3 dot points, right? 3 important aspects that Maxwell utilizes equations for. So the first one is unification of electricity and magnetism, and sort of just justify for that, right? So Maxwell was able to contribute this point because the Maxwell's equation has strong mathematical symmetry, in a sense that if you swap E and B, there will be like identical forms of math. And also we have
Yeah.
this inductive relationship between E and B, making them like actually indistinguishable. Their representation, they're representing like one thing, right, differently. The second contribution is where he used the inductive laws and then thought of this continuous self-sustaining electromagnetic wave pattern. And he thought that if you have an accelerating or oscillating charge particle, that would create a continuously changing electric field, which would induces a continuously changing magnetic field, and vice versa. You just get this electromagnetic wave. The third contribution is where he used the equations and calculated for the speed of this wave and also a bunch of other like geometrical related properties. It was shown that speed of light was very consistent with the speed of electromagnetic wave, demonstrating electromagnetic wave is the nature of light. Okay, so
Okay.
to justify for this, and make sure to write in dot points. Question
Wait,
B.
wait. Do I have to write in dot points or can I just write
It
a
will be
paragraph?
very recommended. So yeah.
Okay.
And utilizing equations. If you didn't use dot points, that's probably fine, but try your best with dot points, okay?
I think I missed one
Uh,
dot point, but okay.
yeah. So all of those three contributions are very important.
Okay.
Question B: how did Hertz's work was able to validate Maxwell's predictions? We had this, AC power source to create this accelerating charge, and then we have this electromagnetic wave forming a standing wave. Yeah. So sort of justify that. Okay. So what I wrote was Hertz utilized an LC circuit to facilitate for a fast accelerating charge. So it will be like the charge accelerates here, where electromagnetic wave production is then verified with a receiver forming a spark on the other side. So
Okay.
receiver received the energy from the producer through the EM wave and produced its own spark. And this observation is evident to Maxwell's second contribution mentioned in part A. So you can also sort of like communicate between the parts of a question. So you don't have to define everything again. So Hertz's work could also verify that. So other than this, right, the fact that we form a spark is pretty much indicating electromagnetic wave can be produced by accelerated charge, and his work could not only was not only limited to showing this, he was also able to show how electromagnetic wave being transversed, as if you can orientate the receiver differently and then see the magnitude of the spark, right? Uh, and he was also able to calculate for the speed of electromagnetic wave experimentally by looking for standing waves in between. Okay,
Okay.
so it was just very nice summary here. Right. So question 12. Newton, Huygens, and Maxwell each proposed different models of light. How does nature of light different among three models? So this question pretty much is like you sort of need to explain, right? So like pretty much the most important thing is to define what each model is saying, and then how are they different. So my approach is to sort of define all of them in three dot points, and then just input some details that like what sort of property does it utilize that light has, which corresponding to this, and also this improvement thing. So how do we get from Newton's to Huygens, and then from and also to Maxwell? What specific phenomena leads to a different model? Okay.
Okay.
So just a little bit introduction. So model of light improves based on like experimental evidences as well as theoretical derivations. Okay, so we've got experiments. We've also got theoretical derivations that sort of engage in this framework of where we improve our understanding of light. So our first one is Newton. So Newton's corpuscular theory of light, define it first, right? So it states that it consists of very small particles obeying laws of classical mechanics, such as conservation laws, right? We're not really assessing the models of Newton itself, so you don't need to be that specific about it. Okay, and then the question didn't really mention any experiments, so you don't need to also be very specific about experiments. So you need to sort of figure out where you're supposed to draw this line of like explaining things in too much detail and then like not enough detail. Right, so you need to find this subtle line yourself by practicing doing more questions. So experiments such as refraction, revealed flaws of the model. So it was just like one line equation. One line sentence justification where like things go wrong and stuff. So I didn't really go into detail how this was like. What was this flaw exactly? I was not really particularly asked in this question. I'm only supposed to sort of just outline and then just mention what's like different in different models. You know what I mean?
Yeah.
Yeah.
Is it better to present this one as a dot point thing, like just
Yeah, dot
intro
point
and
is
then dot
always
point?
recommended. Yeah.
Oh, recommended. Okay.
Is always recommended. Okay.
Oh.
In the HC is always, so as long as you show any sort of understanding, dot point is the best way to show it. Because
Oh.
you can dot points are just secretly split up a question into part A, part B, part C yourself. You know,
Oh, I thought we had to answer full sentences.
it's
Okay.
very convenient for teachers to mark them. It's very convenient for you to read them and for you to be able to structure out your questions nicely. If you just write paragraphs, that'll be it takes effort to structure them nicely because paragraphs are not really, really like they're also connected. You know what I mean? So paragraphs, you need connection between each paragraph. But dot point, you don't really need that connection. Although you could have connection, but you don't need to have that connection. So it makes you
Okay.
easy to structure your answer. Because when we answer those questions, there are typically many different syllabus content that you merge into this question only, right? You know what I mean?
Mm.
So yeah, it will be kind of difficult if you. It will
Okay.
be easier if you use dot points. Okay.
Okay.
Okay. So and then next one we've got Huygens model. I'll just read through. So and then you see how I'm connecting with Newton. So if you were to write paragraphs, you can sort of write those as a paragraph because they are connected. But making it as a two different dot points is like very specific in terms of what you're supposed to talk about in this section. So the failure of Newton encouraged attempts of to model the light with the wave hypothesis, which is guided by Huygens principle. Yeah, this explains wave propagation, and so this is me defining what Huygens principle is about. Explains wave propagation using ideas of point sources, wave fronts, as well as wavelets. This principle is very successful and produced consistent results, which when compared to experimental observations, such as refraction, reflection, and especially diffraction and interference, where constructive and destructive fringes occurred in the Young's double slit interference experiment. Yeah, so how Newton said was kind of different, and Huygens said is different in terms of it can explain more phenomena of light, such as constructive and destructive interference, shown in this experiment, Young's double slit. Okay. So followed by Maxwell. Maxwell is like a much theoretical derivation itself, right? It was then verified with experiments. Okay, so the acceptance of the wave model of light couldn't answer the nature of the wave. So Maxwell's contribution to electromagnetism then summarized mathematical equations for existing laws, which includes Gauss's law and Faraday's law, all the inductive laws. Yeah, also Ampere's law as well. So going from changing B to E and then changing E back to B. So, and these equations allowed predictions where light is made of electromagnetic wave, right, consisting of oscillating electromagnetic electric field and magnetic field, together with the speed of c equals that, and then make sure to draw a diagram. Right, electromagnetic wave are kind of hard diagram to draw, but you can try.
Okay.
Does that make sense?
Yeah.
Oh, good. Question 13. Historical advances in the understanding of light relied on the ingenious interpretation of unexpected observations. So if you read through those questions, many of them are kind of hard to answer, especially this one. And so only 4 marks too. So this is kind of like the HSC way to ask about this question. Not gonna just ask like a normal, just simple definition question. Right? They always want you to think more about the relationship between the models. And this one has a very harsh requirements. It wants a specific experiment that that involves an unexpected observation, and that challenged scientists to change the model or to make different measurements and stuff. Okay, and assess the accuracy of this statement, and then with the reference of one method to measure the speed of light. So not only it implements the requirement you're choosing chosen as experiment, it also requires that the experiment is one of the speed of light experiments. Okay, so the only one, actually, we have two of those experiments that involves an unexpected result. Okay, while the others are all like we know what's going to happen, we're just going to do the speed of light. And those two experiments, first one will be Roma. Yeah, so he was like looking at the orbits of Io, and then unexpected thing to happen, right? The period sort of varies when at different seasons on Earth. That's weird. And then we were trying to figure this out, and then somehow that leads to the speed of light measurement. And then the other one was Mitchell-Morley experiment, where we thought ether exists, and we tried to prove it doesn't exist. And then along the way, it was able to calculate it for the speed of light. Yeah, and then I chose Romer for this one. Okay, so you're very limited to the possible choice for this question. So Romer's
Mm,
method to measure the speed of light is subject to an unexpected observation. So thoughtful interpretations to this anomaly provided measurement of the speed of light. So this is like a brief introduction to what I'm about to say. And then in detail, also dot points, right? So what was the unexpected observation? This observation was the duration of Io's eclipse. It alternates between long and short throughout the year, and that's weird. And then the interpretation made by Romer that was kind of smart, yeah. The ingenious interpretation is the variation of the duration is due to the relative motion made of Earth and Jupiter. Okay, so this one is talking about experiments, so you better go into detail about this experiment. Right? So therefore, so justifying how this is different. So when Earth is approaching Jupiter, duration is measured to be shorter as light and Earth are moving sort of relative to each other. Okay, so approaching each other. To draw this diagram. Okay, where Earth is moving away, and then sort of this light has to sort of travel. It travels a shorter distance when I will come out, so Earth people sees like less amount of time when I was like reaching out. And when Earth is moving away, you draw like the opposite diagram, right? So you will see a longer period in this case. Okay. Now, then
okay.
using the difference in the duration, we can work out how long does it take for light to travel. Okay, and the speed of light. So therefore justifying the validity for the statement. Oh yeah. So this is like a
Okay.
unexpected result. And throughout the analysis of the unexpected result, and then we were able to calculate for the speed of light. And that was just this
Okay.
statement, right? We have evidence. The evidence is Romer's experiment. It's
Should
kind
I
of like
always
English, right?
should I always try and include like a simple diagram of these things?
Oh yeah, if you can, definitely do so. Okay.
Okay. I
If you
see.
can,
Okay.
right? Why not? Because in my opinion, equations and diagrams are much easier to explain things. Are easier method to explain
Okay.
stuff than just sentences.
Okay.
Question 14. This experiment about Fiesel. Okay, so but don't worry, those questions are pretty hard. In actual HAC, it will be like only one or two of these questions. Okay, but they could be on any topic. Could be on module 6 as well. Okay, so just be prepared. So in a bunch of information, right? This is like I said, so people didn't remember the Fiesel's experiments. They need some information for it, and this is if the question explicitly asks for this experiment, they will give you information like this, so you are sort of educated on the spot. Yeah, but we've talked about this, right? So we have 720 teeth. That's like so we have to divide this cog with 1/2 times n, so that light pass through and then return and then hits a gap, and so that it doesn't observe anything. Okay, we want to use the following information and calculate for the speed of light. Right, so make sure to derive for the expression in this specific experiment. And whenever you see a speed of light question, wants a calculation from this. Okay. So the duration for the round trip, right, roundaway trip for this light to pass through this 8.6 kilometers is then just 2 times this L over C. And then while light is traveling, the cog rotates. So the angular displacement for the cog to rotate, and we want the rotation is to go from a gap to a cog, right? To a tooth, right? So that angular displacement is the revolution angle, which is 360, so 2 pi, right? And then we want to split this in 2n parts, and so we divide it by 2n, right? So from a gap to a tooth would be like one part of 2n parts of this whole sort of revolution. Does that make sense?
Yeah.
Yes, this is
Yeah.
what I'm doing. I'm trying to calculate the angle for it. It will be like 180 divided by n, which is just pi over n. Yeah, so also in those equations, the angles are always measured in radians. So that's another thing. so which can be evaluated with rotational speed. So what you do is you pretty much say delta theta is equals to the rotational speed, which is omega, times by the time of the duration. And time of duration can be equated with speed of light like this. Therefore, you would equate those two. Yeah, and then you want to rearrange for the speed of light, right? And then you just calculate, okay?
Yeah, okay.
And then calculate for a percentage error. That's what it's one. So we want to assess the accuracy. And
Oh, I need a
remember that.
percentage error. Okay.
Yeah, assess the
1 sec.
accuracy. That's what it means, right?
Okay, I gotta add that.
So we've got less than 5%, okay?
Okay.
Which is pretty good. Okay. Next one, question 15. So we've got two experiments. As you can see, we've got a double slit interference. We've got a polarization experiment. And then the experiments give you a bunch of parameters, which is a strong indication that you need to do calculation, right? Maybe for this one, but not really for the next one. The other one haven't given me enough information for any. But we can analyze stuff, right? So what I said is, so the question asks, how do the results of experiment A and B support the wave model of light? And your answer include a quantitative analysis for the experiment. Again, dot points, A and B, just two dot points, and do your calculation and then explain what's happening and using properties of light. So experiment A was the double slit interference experiment and it was replicating Young's double slit, right? It was not exactly the same because obviously it's modified. But yeah, just write this down to show you understand, right?
Okay.
So interference experiment, so it validates for the wave model of light as the formation of constructive and destructive fringes, right? As these are wave superposition properties, light is seen as a wave. Okay, that's the reason why we have this wave model confirmation here. With theoretical calculations, we can verify the experimental observation. For example, i.e., finding the distance between the separation and the bright fringe. This is like one way to calculate stuff that I would like to do. Right. So what would they do in order to confirm light is a wave? They would use Huygens principle, derive this theory equation, and then calculate for something, and then use an experiment to measure that. If the results are matched, we're good. Yeah. So we just do this calculation and we end up this with like the fringe separation is 2.7 times 10 to the negative 2. That was the previous booklet, so hopefully it was easier enough to understand. Recall that maximum in the double slit interference is the sine of the angle equals to m lambda. M is the order, so you just pick m equals to 1 for adjacent ones. Okay. With small angle approximation, you could substitute sine equals to 10, which is like the distance of the fringe separation over the distance of the screen separation. Okay, so y will be something like this. Yeah.
Okay.
Okay, so for experiment B, it will be like a polarization experiment, and then from the result, we can see how we've rotated the angle of polarizing axes. At 0 degrees, we see intensity change. At 50 degrees, we don't see an intensity change. All right, so this is very crucial because we would know that the polarizing axis for our light, it will be polarized, right? And it will be polarized exactly when it's 50 degrees, you know? That's why when the polarizer is also 50 degrees, there's no change in intensity. So you sort of mentioned that.
Okay.
And so from that, you can calculate how much intensity has changed at 0 and 140. And then that's what calculation I choose to do. You can choose whatever calculation you wanted to do as long as it fits the experiment. I just happen to choose this one, okay? You have the freedom to do that in this question. So experiment B, in contrast to experiment A, B has demonstrated polarization of light. The polarization state of light is the state of electric field orientation. So that's defining all the stuff, right? So on top of showing light is a wave, it also shows light is electromagnetic since polarizers are made of materials that constrain the orientation of electric field oscillations. The second thing is light is transverse, right? So it only has to be a transverse way to be polarized. Otherwise, polarization doesn't even apply. As direction of propagation is perpendicular to transmitting axis, which is electric field oscillation. So the result shows the varying intensities. This is referring back to the result. the very intensity as polarizer rotates at 50 degrees to the vertical, there's no change in intensity. This would indicate that the laser source it must be polarized to an angle of 50 degrees. Okay, and hence we could use Malus's law, and we can evaluate for the transmitted intensities of other angles. So just sort
Okay.
of do at 0, at 140 is the difference between 50 and this angle, right? So 50 and this angle will be 50. 50 and 140 it will be 90. So that one will be actually you get 0 intensity out of it. Okay,
Okay. Do
so
I
just
have
calculate.
to write to like this extent of detail when they only give me that many lines?
Uh, so the
I
philosophy
mean,
is to
this like
always
oh
always
yeah.
write. Look at this mark. This is 9 mark. You're supposed to have
Oh,
three
okay.
pages about this. Okay. So
Oh,
HSC
so this
only
is just
give
cut
you
short. Okay.
so the when I write those questions, I just put as like 2 times of the lines of this. So I just put 18 lines. That's like the way we produce the materials. But HSC
Oh,
they will always they will give you like a shorter lines, like smaller amount of lines. You will always exceed. Okay,
okay.
so the philosophy is I think they have like specific sample answer that would only require this much lines. But the thing is, we just have freedom to answer all those questions, and then it's kind of unclear of what exactly they need for all those questions. Okay, so the
Okay.
safest method to trying to get full marks for those is to write as much as possible, um, and structure as possible, so you are less likely to miss out anything.
Okay.
Yeah, so that's like my approach.
Okay.
So typically people just write so much for this, and they just ask
I
for
see.
many booklets. But don't worry
Oh,
about not finishing with enough time, right? So it's like from my experience with physics and chem 3 hour tests, we always finish like if you are good enough, right? Band 6
yeah.
students always finish uh at least 30 minutes before the end of the test, and then they always like ask
Right.
for
Okay.
like 5 extra pages stuff to write, and so
Oh my
it's
God.
completely okay with time. Okay, as long as you do the easier question fast. Okay, with all the easy calculations, like one step calculation, that's pretty easy. And
Okay.
there will be those questions. It's just that in my homework I rarely give out all those questions because they're pretty easy. There's no
Yeah.
like you do once, that's probably it, right? You don't need practice for them.
Okay.
And then next question will be question 16. I'll just finish up with everything here. Okay, it's 2 questions to go. Actually, we're not gonna. Okay, so question 16, we've got this polarization experiment where we sort of rotate this polarizer, and then we continuously measure the intensity, and then we measure the angle. So it's like the experiments where independent variable is the angle, and then intensity is independent variable. Is the dependent variable. We plot them. Okay, and then this line is representing the equation uh where it's I equals to I naught times the cosine square of this. So the gradient will be I naught, right? Does that make sense if you recognize this?
Yeah.
Yeah. So if you do that, and then using the graph, calculate for the so sorry, the gradient will be I naught over 2 because that's unpolarized light. So here will be I
Okay.
naught over 2 over 2. Okay. Yeah, so you just sort of apply that and then calculate for the gradient and get your final value. Okay. This
Okay.
question isn't that hard.
Yeah.
And then the next one, this one is a big boss. So talking about the
Ooh.
Huygens model of light, it's pretty obvious, and talking about the Maxwell's models of light. So
Mm-hmm.
question specifically wants so what role of experimental observation have in the like experiments have in the development of these acceptance of scientific models. So in contrast to the question we did before, which didn't really ask about any experimental observations, question 12, right? This one wants you to also mention in a good detail of experiments. You can see how I mentioned a bunch of experiments, quite long this one.
Yep. Okay.
Um, yeah, so again, dot points, one dot points, model A, model one, and then bunch of experiments. I talked about refraction. I talked about the Young's double slit interference experiment, drawing a diagram
Mm.
showing all the wave properties,
Can you
and
send this
then
doc to me later, perhaps?
yeah, I can do
Just as
that.
reference. Okay.
Yeah, I'm also sort of recording this section.
Oh, okay,
I'll
okay,
send the recording to you as well.
okay.
And we have model 2, which has like these experiments to the Hertz experiment and also the polarization. It's just because this one you have to mention in detail what's happening for each experiment. That's why we have a lot of things to do. And
Okay.
I mean, the question is also pretty harsh. 2 experiments each model. That's why it's long.
Uh, okay, that's why. Okay.
It's like a grand summary of this booklet that we're doing. Okay.
Yep.
So yeah, yeah. So this model 1 is Huygens model, and was able to just pick any 2, right? You could pick reflection as well. I just happened to pick refraction because then I can reference something that's not required, and hopefully would sort of like amaze the marker, right? So I can say that Newton was not able to do this, right?
Yeah.
Just like one sentence
Okay.
talking about the particle, the rejection of particles model. Um, yeah, and double slit, just constructive and destructive fringes and all that. And then model 2 was like this more advanced model of the wave model, right? It was on top of Huygens model fly. We demonstrated exactly what that wave is, right, by Maxwell's theoretical contributions and verified by Hertz experiments. And then also polarization. So it's just what we've been talking about, okay?
Okay.
All right, so the challenging question, I'll sort of just go through this quickly, okay? So if you know that to polarize an unpolarized light, there's 2 different ways to do so. Light
Mm-hmm.
can also be polarized through reflection of like a liquid surface, usually water.
Oh,
Okay,
okay.
so light from the sun are always unpolarized.
Mm-hmm.
When light from the sun hits water, 2 things happen. One is the reflection, the other one is the refraction. Okay.
Mm-hmm.
So I'm drawing the unpolarized light like this. So we have electric field oscillating perpendicular to the wave of propagation. And then we also have another component that's sort of going in and out of the page, which I use a dot. Okay.
Okay.
So that's like an unpolarized light here. Okay. When it hits the surface of water, 2 beams of light are sort of being separated. So you can sort of think of this polarization state is the addition of this and that together.
Okay.
Okay. So
Okay. Yeah.
therefore, question A says to how can a light be partially polarized? So if you have observed here, this beam of light is like slightly less unpolarized compared to this one because it has another unpolarized component being split out into different propagation direction. That's the refraction bit. Yeah.
Okay.
All those, okay, those 2 reflected and refracted are still unpolarized, but they are less unpolarized because they are sort of components of this one. Okay. All right.
Okay.
So, and then question B investigates, is there like uh, is there like a what's that is there like a specific angle where you're supposed to observe the lights, the reflection, right? So that the reflected beam is fully polarized. So if you think about that, there is that such an angle, right? So that angle would correspond to when the refracted beam is perpendicular to the reflected beam. Okay. So we know the refracted beam must have an electric field oscillation perpendicular to direction of propagation, right? So that's this direction I'm drawing here.
Mm-hmm.
If this line is perpendicular to this line, you see how this electric field oscillation is then parallel to the direction of the reflected beam.
Yeah.
But electric magnetic wave are transverse, which means that the reflected beam must not have any electric field oscillation in this direction.
Oh,
Okay,
okay.
which means it can only have an electric field oscillation that's into the page and out of the page, sort of like, and that becomes polarized because now the electromagnetic wave goes like horizontally. Okay,
Okay.
so you can polarize it like this. And so at what sort of incident angle? We call this angle theta B. B stands for
Mm-hmm.
scientists for Brewster's angle. And we would have this perpendicular like thing forming, and that's what question C is to try to prove for this. Okay. Which
Okay.
involves the Snell's law, which then you just rearrange from the Snell's law, and then you would know how theta 2 at like this angle is 180, and that's 90, and this angle is related to theta 1, which is the Brewster's angle, and then you can do your math and subtract everything out. Notice how sine of pi over 2 minus theta b is just cosine theta b. So you can substitute that in and you can rearrange to get a tangent. So that's how you would derive for it. Okay.
Okay.
Yeah, it's quite complicated, but so yeah, I mean, I'm thinking that they could ask like a question in an HSC about Brewster's angle. They tell you what it is and then just let you figure it out. Not as difficult as this one because they will definitely give you more information than what I'm requiring here. They probably won't let
Okay.
you to show this. They will give you this equation that you calculate for something maybe. Certainly, they could ask you to explain how this can be fully polarized. If
Okay.
they tell you from like if they draw the diagram for you, like if they actually draw this diagram, and then so you can see what's going on.
Okay.
Yeah, yeah. So just know more than the syllabus, like know a bit more than that. It would be a very good
Ugh.
way to prepare for HSC if you want to have like a
Okay.
high band 6. Okay.
Okay.
Anyways, that's enough for this booklet, and the homework will be just try to finish the other booklets. Okay, so the Ewing
Okay.
booklets. Okay,
Yeah.
right. So I'll see you next
Okay.
time.
Thank you.